Welcome back, dear friends. In our last video, we learned about seeing neural networks as computational graphs, frameworks in which data is passed along complex ramifications through nodes or intersections, which lead to multiple information flows called edges and the dependencies that control them. Propagation, or the process through which data or execution signals are transmitted from a parent node to a child node, with the purpose of generating predictions through three core components: the weights, or the strength between connections, the activation functions applied to a neuron's output to determine how strongly the neuron reacts to what it receives, and the biases, or the values added to help the activation function shift the output so that the data fits better. In our growth journey, we discovered that transformation does not happen through intensity, but through systems. Microhabits build familiarity, familiarity builds safety, and safety allows identity to shift without resistance. The habit must be so small that the nervous system does not perceive it as a threat. 2 minutes of stretching, 1 push-up, 1 page of reading. The power is not in the size of the action, but in its repetition. And repetition is precisely how neural networks learn. We previously established that the purpose of forward propagation is to generate a prediction, an output. But prediction alone is not intelligence. What truly creates learning is the correction of error. The accuracy of a network's predictions depends on how well its weights and biases are calibrated across the entire data flow. And this is where something remarkable happens. Once the output is produced, the child node transmits a signal backward, reporting the difference between what was predicted and what actually occurred. This difference is called the loss. But the loss is not merely about magnitude, how wrong we were. It also carries direction. Were we above the target or below it? In fitness, this is like adjusting caloric intake. If we eat too little, we feel faint and lose strength. If we eat too much, we gain unnecessary weight. The error is not just how far we are from balance, it is whether we overshot or undershot. Learning requires knowing both. Both weights and biases are adjusted iteratively to minimize this loss. This process is called optimization, and the core mechanism behind it is backpropagation. Backpropagation moves in the opposite direction of forward propagation. While forward propagation turns inputs into predictions, backpropagation turns errors into learning. To properly correct the error, the network must account for both its magnitude and its direction. This is achieved through gradients, vectors of partial derivatives that measure how sensitive the loss is to each parameter in the network. In practice, as developers, we only define how the forward pass is computed. The heavy mathematical work of computing gradients is handled automatically by frameworks such as PyTorch or TensorFlow through a process called automatic differentiation. The actual adjustment of parameters is performed by an optimization algorithm known as gradient descent. The wisdom of gradient descent resembles the psychological concept of our window of tolerance, the zone in which growth is possible without overwhelm. The most intuitive metaphor for gradient descent is walking downhill on a mountain slope in the dark. We cannot see the entire terrain. We can only feel the slope beneath our feet. Each step gives us feedback. Is the ground descending? Are we slipping? Are we stable? This step size is equivalent to the learning rate, the amount by which the model adjusts its internal parameters in response to error at each iteration. The learning rate is calculated between two core constraints. This takes us to some key requirements. Convergence, which occurs when the weights and biases have been stabilized and the loss function stops decreasing. Psychologically, convergence resembles integration. The behavior no longer feels forced. The identity no longer feels rehearsed. Stability replaces volatility. The training time represents the total duration required to reach convergence. And just like in personal growth, rushing rarely accelerates integration. If the learning rate is too small, the model gets stuck in a slow convergence, requiring a larger number of iterations. Progress becomes painfully slow. Convergence takes a long time. Psychologically, this resembles under-challenging ourselves, staying so comfortable that growth is minimal. We may feel safe, but we remain underfitted to life. A small learning rate also risks trapping the model in a local minimum, a point that appears optimal within its immediate surroundings, but is not the best possible solution. Psychologically, this resembles settling into a comfortable but limited identity. We improve slightly and mistake proximity for mastery. The global minimum, on the other hand, represents the true optimal configuration, but reaching it may require temporary discomfort or even climbing upward before descending further. Growth is rarely linear. If the learning rate is too large, we risk overshooting the minimum entirely. The system oscillates. In human terms, this is the cycle of extreme motivation followed by burnout. We take giant leaps, exhaust our nervous system, then collapse. The learning rate can go from 0.0 to 1.0. Conventionally, it is initially established at 0.001 and increased incrementally. A constant check for convergence could help us select the best learning rate. Never forget, our goal is to have the cost function decrease rapidly and stabilize. Therefore, we can set a fixed learning rate that we maintain throughout the training, but often, adaptive strategies perform better. As strategy, we can choose to either decrease or increase of learning rate based on time or performance. Time-based decay reduces the learning rate gradually, according to a predefined schedule. Psychologically, this mirrors how early enthusiasm stabilizes into sustainable discipline. Performance-based decay adjusts the learning rate depending on validation results. In life, this resembles self-awareness, accelerating when momentum is strong, slowing down when stress accumulates. Once we can get our nervous system familiar to the micro-habit, we focus on 1% improvement daily. Hyperparameter techniques that could help us find our learning rate include the grid search, which identifies the best value within a specified range, and the random search, which samples values from a probability distribution. The learning rate can also be adjusted dynamically within the training process through specific algorithms. Why do we need any of these algorithms when we can use the gradient descent? Well, the regular gradient descent adjusts every parameter using the same learning rate. These optimizers say, wait, not every parameter should move the same way or at the same speed. As algorithms, we can use iterative, takes the frequency behind parameter updates as reference for adjusting the learning rate. Iterative increases learning for infrequent parameters and decreases it for frequent ones. Psychologically, this resembles focusing more attention on neglected areas of life rather than over-polishing what we already do well. Let's say we're preparing for an exam which covers 5 disciplines. We practice math every day, but barely touch history. Iterative adjusts our study schedule to give more energy to history. Over time, it balances things out. Its limitation is that it keeps reducing the learning rate over time, until learning almost stops. Like someone who becomes so cautious, they stop progressing. RMS prop divides the learning rate by a moving average of recent squared gradients to stabilize updates. RMS prop stabilizes learning in changing environments by smoothing fluctuations. In human terms, instead of judging yourself based on everything you've ever done, you judge based on your recent performance. You don't let mistakes from 3 years ago dictate today's confidence. Adam, a very popular voice, Adam reflects the advantages of both iterative and RMS prop together, computes adaptive learning rates using estimates of both the first moment, mean, and second moment, variance, of gradients. Adam balancing momentum, remembering direction with adaptive scaling. It adjusts learning rates individually, remembers past direction, and smooths noisy updates. As the go-to optimization algorithm, Adam is like someone who learns more where they are weak, doesn't overreact emotionally, remembers long-term direction, adjusts intelligently based on both pattern and recency. It's disciplined and adaptive. Neural networks learn through repeated, calibrated adjustments, not dramatic transformations. Likewise, identity shifts are built through habits that are obvious, attractive, easy, and satisfying. As James Clear reminds us in Atomic Habits, the goal is not intensity, but frictionless repetition. Over time, good habits require less energy. What once demanded discipline becomes automatic. And when we look back at challenges we once believed impossible, we gather evidence. Evidence reshapes identity, and identity reshapes future behavior. In our next video, we will explore how motivation interacts with activation functions, and how intensity of response determines transformation.